I did it in a one-liner just to be clever. So we can see it. So what I did is I indexed out the value, and I did it wrong. Hits, bases on balls, hit by pitch, and intentional bases on balls. We don't need intentional bases on balls. Let me alter this slightly here. I used the wrong formula. And I screwed it up. Let's see. Oh. Oops. Break this down here. All right, so I'm going to break it down and try to figure out where I messed up. So I indexed out the top part here. And so I've taken hits, bases on balls, and hit by pitch, and I sum them up on axis equal 1. That's where I screwed up down here. And then I'm going to use the division method. Okay, so I'm going to take that and divide it by something else, and that something else is the denominator. So should be at-bats, bases on balls, hit by pitch, oops, not hits, and sacrifice flies. And I've added a very, very tiny number just to prevent divide by zero stuff, okay? Because some, again, pitchers may not have had at-bats, relief pitchers in particular. I think what I forgot here is axis equal 1. Okay, so I add those up, divide it, and then I'm going to order it ascending in descending order, excuse me, and it didn't work. What did I do? 1, 2, 3, 4. Oh, got the sum on the wrong side of the division. This highlights why it's not always a good thing to do everything in one line. Do baseball. What's that? There we go. Except I got nans. I got to add my. You get the idea. Okay. All right. I definitely should have broken this up into multiple sheets. But anyway, so in that baseball example, what I did to create this unique index rather than having just an integer index is I concatenated in sort of a kludgy way 3 fields to make them unique, which isn't really how you want to do something. A more elegant way would be to create what's called a hierarchical index. And I showed you this when I imported that microbiome file earlier on. So I want to combine year, team, and player. And what I do is I simply set an index that is composed of 3 columns rather than just 1. And what this creates is yet another index object called a multi-index, which all it is a sequence of tuples. And within each tuple is each element corresponding to the columns that I combined. Okay? And this one is indeed a unique index. All right? So now I can index out Julio Franco playing for Atlanta in 2007, just like that, okay, as a row. So and this is what I did earlier on. I specified taxon and patient. And so taxon by patient, we get unique a unique index that looks like that, okay? And of course, the nice thing is that we aren't bound to, indexing out every single element of the multi-index. You can simply index out, for example, just the proteobacteria and leaving alone the patient. Okay, you don't have to use both elements of the multi-index, which is nice. And in fact, we can create them on either axis. So here's just some trivial data where we've got A's, A, B, and then 1, 2 on the main index. And then on the columns, we've got states and colors, okay? Just, again, some trivial data. And so we've got a hierarchical index here. So it's A1, A2, B1, B2, and then a hierarchical index here, Ohio green, Ohio red, Colorado green. And in fact, we can, label the indices. So state and color, key 1, key 2, okay? And, index it however you want. If you just want the A and Ohio, we do A and Ohio. B2 of Colorado, we get B2 of Colorado, which is just a scalar value, but notice it gives it to you in a series. If you want the inner index, we want to swap the levels. So here what I'll do is I'll swap patient to the outside first and index out just the patient. Okay, and so I can, again, do stuff like sorting. So I'm just sorting by patient in descending order, and then the other one is left in the order that we placed it in originally. Okay. Yeah, we did missing values earlier. Just a couple of things to add to that. So these are sort of typical, missing values that you might use, and it recognizes, two of them automatically as being missing values. The others not, and we can either drop those if we don't want to use them. So drop NA. That drop NA method will get rid of firmacutes. Or we can do it this way. We can say which ones are not null. Not sure why you would do it this way, but you can. Not null is a useful method. By default, the drop NA method gets rid of the entire row where one or more values are missing. So if we do drop NA on this, it doesn't. What else can it do, right? You want to drop NA, so drop them. But you can customize this. By specifying a how argument. And so all means that it only drops one where every field is missing. Okay, not in this case, but in that baseball example where I added blank rows, that would have worked. Or you can get even more granular than that. You can establish a keeping threshold. And so if I say thresh equals 4, it retains all rows that have at least 4 columns not missing. So in this case, it's only going to drop that last one, and it's going to keep the one before it. So it doesn't say which ones can be blank, but it gives you a little bit more granularity. And again, we can drop NA in either direction. So if we want to drop columns. Rather than dropping missing values, we can populate them. So fill NA fills it with whatever we pass it. You can pass it a dict for, obviously you want to do different things to different columns in some cases. And one thing to be aware of is that fill NA doesn't manipulate your data in place. It returns a new object with the desired filling behavior. Okay, it doesn't do it in place. So the original data still looks like that. You can specify an in place equals true argument, but it's not great practice. Particularly, sitting in an IPython notebook and you make a mistake, then you got to go back and re-import your data. And it's always good to do these things in sort of a functional programming style. Okay, we've seen backfill, so this filled it backwards, or in some cases, and we'll see in one of the examples if I ever get to it, we can fill it with the mean from the non-missing values. So Firmicutes was filled by, even though it was missing for one particular value, it filled it with the mean. And notice it had to change everything to floats. Okay. Data summarization, quite useful. If we want the sum, it's going to do sums by columns initially, which doesn't make a lot of sense right now, right? So in some types, so if you sum strings, what does it do? It concatenates the strings. But here are all the bases on balls, all the strikeouts, and so on. Some methods are meaningless if you try to, you can't take the mean of strings, and so it actually drops those object-typed columns in that case. Okay. So if we take the mean of this guy, it's going to account for the nan, and by default it skips it. But again, we may not want that. We may want to raise, we want to return a nan or something that gets caught later on. It's up to you. And then axis equals 1. It's probably more meaningful in this. Maybe not. Summing over rows. We're summing over the extra base hits. So these are the numbers of extra base hits from each player, and I've sorted them in order. Had a question about this earlier, and if you want to display something other than just that summary table for a large table, what you can do is describe it. And describe will supply some brief summary statistics for every column for which it is meaningful to do so. So again, the string columns are omitted here. So counts, means, standard deviation, and a bunch of quantiles. Okay. Describe gives you some interesting information sometimes about the non-numeric data, how many unique values there are, the top, the most frequent value, etc. And then summary statistics, so covariance, if you want to know the covariance among the home runs of all the players. It's the covariance of home runs with doubles. So 70% covariance. Sorry, it's not 70%, it's just a value of 7. If you want to convert it to something that's a percent, you want to do the correlation. So it's 78% correlated. So it takes the covariance and divides it by the square root of the product of the standard deviation. Okay, so they show basically how one column increases or decreases relative to another column, how they're associated. Okay. So at-bats and hits, very highly correlated, of course. And then if you just call core on the whole data set, you get a big matrix, and again, of the numeric variables only, where it's 1 along the diagonal because everything's perfectly correlated with itself. And then on the off diagonal, it's really just a triangular matrix that's reflected here, right? What else have we got here? Oops. So if we take one of our microbiome examples here, we can apply some of these summary functions to a particular level. Okay, so we're going to sum according to taxon, but we're not going to respect patients. So we're summing over the patients essentially. Okay. Yes.
Is there any way to list how many objects you have already created? Like, say you make copies and change them, and you have all that stuff
In your memory?
Yeah, like in R or something where you shows like all the names or all the stuff in there.
Yeah. Was it DIR?
What about
Oh, who? There you go. Oh. No. This is an IPython thing? Thank you. Cool. I should use that more often. Writing data to files, I think this is the bottom of the file. Similar to the read, there's complementary to's. So we're writing, to a CSV file. You can specify things about delimiters. It doesn't have to be comma, but it's comma by default. How NAs are represented, and whether or not you keep the index or not. One efficient way of storing data to disk is in a binary format, namely the pickle. So we're going to pickle things. So we have to pickle and read pickle. Okay, you bring it right back up again. Okay. Those are the basics of pandas. Any questions at this point before we keep on moving? All right, so let's move on to the second notebook. Clear these guys out. And I'm going to restart my kernel. And what version of Pandas? Oh yeah, it may have load. You might try load. Yeah, that's a recent change. Yeah, I'm using 0.11.1, I think. All right. Onward. So a few more advanced stuff, topics here as we get more into some less trivial data manipulation. One thing that's always good to know about that Pandas does really well, again, because it's optimized for doing time series analysis, which implicitly has dates and times associated with it. Date times are hard, okay, because time is weird, right? There's different numbers of days in each month. There's leap years. There's time zones. There's all of these things that make it difficult to deal with dates and times. And so you can either ignore those, depending on the type of analysis that you have, or you can use some sort of package, either built-in or third-party, to deal with dates and times. And so the date-time built-in library does this sort of temporal information handling quite well. So if you say date-time now, it gives you an object that has several attributes related to the time right now, all the way down to milliseconds, I guess. And that object has several attributes. So if I want to know what the day is, I can just index that out. The day of the week, for example. And I guess it starts on Monday with a 0 and Tuesday is a 1. There are simpler objects if you only want date or time rather than date time combined. We can do that. So 324 and an arbitrary date. It's my birthday, so now you can send me a birthday card. And it returns, so it returns the number of days, hours, and seconds, I believe, since my birthday. So I'm just going to carry that around with me if anybody asks my age, I'm 15,636 days old. Right, so those are very useful, and we'll see how we can use those right now, in fact. So we're going to use another real-world data set that's neither baseball nor microbiome. This is some data that's collected by the Coast Guard on every single ship that traverses through U.S. waters. So they've got most vessels now are required to have what are called AIS, Automatic Identification System, transponders on their boats. Speaking of data tracking, they do it for ships too. And every so often it sends a frequency to these AIS receiving stations, and all of this data are stored. And so it's a very good source of very big data. So big, in fact, that we're actually going to use a summarized form of it. So this is included. One of the tables is called transit segments. And this segment includes entries for records of ships passing through particular administrative areas in and around the waters of the United States. And so we have a MMSI number is a unique identifier for a ship, and then it's got a name, and for some reason the same vessel has different names sometimes. Which transit this is, what segment it is, how long that segment was, I assume in kilometers, and then average, minimum, and maximum speeds in knots. A statistic having to do with what percentage of the time it was greater than 10 knots, and then some date time information. So the start of that transit and the end of it. Okay, so a nice little data set to chew on for a little while. Okay, so we'll get into plotting a little bit later, but Pandas includes some very high-level plotting methods. In this case, we're going to look at a little histogram of segment length to see how they're distributed. And we see here that most of the transits appear to be quite short, but there's a whole bunch of, or a few, relatively few longer distances that actually make this kind of hard to look at. So we'll log transform by doing apply NP log and then doing a histogram. And we can see that the log distances kind of look like that, okay? And so we've got these date time fields in here, but unfortunately they're not date time types, okay? Didn't know what to do with them right out of the gate from importing it using read CSV. So what we got to do is convert these to date time. So we're going to go into our date time module and use strip time, and just for a particular example, just look at the first one, and you just give it a format. So it's month, day, year that are slash separated, and then the space between hours and minutes, and it'll read those in as datetime objects. There's a dateutil package, another built-in package that includes a parser that tries to figure out what it is for you in case you don't really feel like doing that manually. Okay. And we can do this to a particular column. It's quite a big data set, so it takes a little time to chug through it all. Yes? That didn't get a plot? What did you get? Okay, so it did plot it, you didn't get it in your IPython notebook. So you have to do what? Percent pylab inline or something like that? What you might want to do is go back and restart IPython. That's what you do, right?
Also do a percent pylab at the very top.
4%. Oh, at the top of your notebook, yeah.
Or you can just make a new cell and run percent pylab space inline in it.
But that doesn't work.
I think it works depending on which version of IPython you have, I would imagine. We have experts on the.
The last session, their backend set wasn't set right.
Okay.
So they set the AGG and don't split plot.
Doesn't like AGG.
Well, it says backend inline, but doesn't work.
Just like that. I will forge ahead while they attend to those. that should be most of the plotting we do until the next section. So we have a little time to figure it out. Pandas does have a toDateTime convenience function here that sometimes, well, usually works. Can be unreliable depending on how weird your data is. But for this, it does a pretty good job. And it takes even longer. Poor little MacBook Air. There it is. And there's a custom NA value. It doesn't use NaN, it uses NAT, not a time, for reasons that are, I'm sure, known to Wes.
Quick question on that.
Yeah.
That convenience function. So that includes ideas of internationalization as well.
I'm not you know what? I'm not sure about that. How good of a job it does with in terms of UT time zones and so on.
Yeah, more like names of parts of foreign languages.
Yeah, I don't know. I haven't played with weird international dates like that. So I know DateTime will do it. So I usually try this first, and if I get something sensible, I stick with it. Otherwise, you have to. It takes a little more manual labor. So, yeah.
Is it possible to transform a column, data frame column, or a series into a datetime?
Yep.
Not the datetime 64, but not the numpy.
So this is a series, and you see the D type down here. It's datetime 64.
Yeah, that's the numpy, and it's errorless. So I need
Oh,
the actual datetime, not the datetime.
oh, I see. Let's. Right. We tried casting it over.
I don't think there is a casting.
Yeah. Yeah. The book has a lot more. I don't have a lot of experience using using different time formats, and I just stick with whatever Pandas gives me. So it's probably best to consult the book on that one. Does anybody else know anything about that? And you don't want datetime 64?
Sometimes it doesn't order the date correctly.
Oh, okay. Huh. Yeah, that's a good question for Wes. One of the really nice features of data frames is the ability to merge them with other ones. And so this is a good example here. We've got information already loaded on the segments. So these are, again, transits of individual vessels over a number of years or a number of months. It's actually, I think, over about a three-year period. So a lot of these ships have come through multiple times. But we may want to include some more information about the ships. And so there's another table here called vessel information, which is much smaller. And it includes things like whether it's a sovereign vessel, which flag it is, what type of vessel it is. Some have multiple types for some reason. So one's a military dredge for towing or something like that. So, if you want to see the unique ones, I can filter them out by looking at unique vessels, and then I'm going to get rid of the ones that have multiple types by filtering out these slashes. So we can see there's a wide range of vessels. And so we may want to associate this vessel information with the different transits and see how maybe the behavior differs from ship to ship or by ship type. Okay, and we see that most of the traffic is cargoes and tankers. This is off the east coast of the United States, by the way. So there's sort of 10 or so that account for most of the traffic, and then lots of singletons. So what we have here is a situation in which there isn't a perfect one-to-one match between the two tables because some vessels have more than one transit. So this is what's known as a one-to-many relationship, if you're familiar with databases. And in Pandas, we can actually combine tables that have these sorts of non-one-to-one relationships. So what we're going to do, here's just a simple example, so a trivial example here. So we've got two tables, one with age and ID, two data frames, age and ID in one, and then ID and score in another, okay? So these could be test scores or something like that. And if we simply use the pandas merge function, what it does, it makes some decisions for us. It merged the two data frames using the field that they have in common. Okay, so they merged on ID. And so without any other argument, it uses any common column names as the keys for merging them. And notice also that ID equal to 3, which is up here, doesn't show up here. And the reason it doesn't show up is that there are no ID equal to 3 in the second table. So this does what is known as, by default, as a inner join. And by inner, it essentially means the intersection of the two tables. It's the things that are in common only. And merge has several optional arguments, one of which is the how, which allows you to tell it what kind of merge to do. And so an outer join is the union rather than the intersection. So it's all of the elements in both tables, and then, of course, the only thing it can do for missing ones are to include a nan there. All right? Can also do things like right and left joins that includes, for example, all the rows from the right tables, but only the intersecting ones from the left, and vice versa. Okay. So let's look at our real data. So here's one line from segments and the other from vessels, and we can see it's interesting here because we have MMSI as the obvious one to use because I told you that it's a unique ship identifier. But in this one, it is a column, and in this one, it is an index. You'll notice that's the way we imported it because this vessel, the vessels table is unique. It's one row per vessel, so I could use it as a unique index. Here, I could not. So we can totally customize merge to make it do what we need to do, and what we employ here are the arguments left index and right on. And so right on means on an index, or sorry, on a column, excuse me, and left index is as the name implies on an index. And of course there's the corresponding right index and left on. But so in this case, we're telling it that we're using the index of the left table, being this one, the first that we list, and then a particular column that isn't necessarily an index on the right column. And if we execute that, we absolutely get the merged table that includes the columns from both tables, and including MMSI. What you will notice is that it's no longer an index on the merged table. We look at the index here, and it's starting at 0, and it's just a numeric index. So it can't use that as a unique index anymore. All right? There is a merge method as well as a function. Get used to this. There's a lot of functions with corresponding methods in pandas. This is one of them. So vessels automatically becomes the left table, and then the one we pass in here is the right one. So we're taking vessels, we're merging it with segments, and it does exactly the same thing. Okay. Something that usually comes up is that tables may have the same column name, but you may not want to use them as something to merge on. They may mean totally different things. So, for example, we could add type to segments. It wasn't included there before, and the reason I'm adding it is because there is one on the other table, and you'll notice what it does is it renames them type X and type Y, where X is the left table and Y is the right table. So it maintains them and then it identifies them. And you can identify if you don't want X and Y, there's a suffixes argument that you can add to do a custom suffix. One other manipulation that you often want to do is concatenating. So you've got a data table that grows as you collect data, for example, or columns are added, new information is collected that wasn't collected before. And in Numpy, of course, we have the concatenate function that takes a list of Numpy arrays, so just some random arrays, and then the functions for row and column concatenation, R underscore and C underscore. Those are very useful, often called binding or stacking. But of course, Pandas, we have something additional to worry about because it does this automatic data alignment. Hold on one sec, my battery's about to die. Yep, this one works. Would have been tragic. All right. So yeah, Pandas has indices to worry about. So let's see how this works. We're going to go back to some of this microbiome data. So there's a whole slew of microbiome data in the microbiome directory, and they're just numbered sheets. And so we're going to import 2 of those. Okay, and they're of different lengths. So some patients had some species or genera or taxa that other patients didn't. What we have here, the names are identified right down to the genera. So this domain, kingdom, phylum, King Philip came over for good spaghetti, if you remember from your biology class. Big, long, uniquely identified taxon. And so now we're going to give these meaningful labels, count and taxon. So now they look like this. So yeah, here's how they're named. It's in this order. And this is what the index looks like, of course. So it's kind of a long index, but it's unique. And so if we can use the concat function to concat along axis 0, which stacks them up, right? But of course, that index is not going to be unique anymore, right? Multiple rows will now have, or multiple values, or single values will now have multiple rows. If we concatenate axis equal 1, it concatenates column-wise. So, but it respects the indices. So it's a little bit hard to see because, again, the length of the indices, but there's a column for the left table and a column for the right table, MB1 and MB2. And it's a little easier if you just look at the values. So this taxon was only in MB2 and wasn't in MB1. This one was in both, etc. And we can, if we only want to know the overlapping ones, of course, we can do an inner join, right? Even though we're using concat instead of merge, it'll still do ones for which they are included in both data frames. Or we can do clever things like use the second table to fill values absent from the first. So we do combine first. Okay? And what we get is a single column that essentially fills in the values from the absent from the first table using the second one. Okay? We could do things like create a hierarchical index. So we got patient 1 and patient 2. Again, a little bit hard to see. But that's a unique index because patient by taxon is, patient by taxon is going to be unique. Or we can use the dict, concatenate by supplying the data frames as a dict. So even if you don't start with a data frame, we can pass that data in. One thing to note that's useful, if you want it to operate like NumPy concatenate and just ignore the index, which is sometimes useful, you can do ignore index equals true, and then it will just smush them together. So this is an exercise that sort of a real-world exercise where we're going to take the data in that microbiome subdirectory, and there are 9 spreadsheets in there, and a 10th file that contains some metadata. What we want to do here is write some code that imports each of the data spreadsheets and writes them to a single data frame, and then add columns from the metadata that correspond to each of the files so that you have information on the patient that each of them came from. Let me give you sort of 5 or 10 minutes to get started on that. We're at 3 o'clock right now. And though the hands-on stuff is good, I do want to make a little bit of progress here. So I'll let you get started, and then I'll give you some answers. Yeah?
So which version of Pandas introduced read Excel?
Read Excel? I think it was 0.11. So you can, if read Excel doesn't work, you have to do the 2-step process, which is, it's read where you import the Excel file explicitly, and then you do the parse. You have to, yeah. Let me pull that up for people just in case. There we go. So it's Excel file and then parse. So one is called metadata.xls. It looks like that. Okay, and so it shows a group that they came from. So some had NAC, which is a disease, necrotizing enterocolitis. Some are controls. And then samples from the tissue and the stool, and then the file that it came from. So you want to add columns corresponding to those. And do get up and take a break if you need it.